This section is on application questions. The math in this section is the same as the previous section, but now we are asked application questions, so there is a context to the equations and inequalities. For example, let's say we are running a business that sells two different products. We'll let X be product 1 and Y be product 2. So there are many things to consider. Each product sells for a different amount of money. Each product takes a different amount of time to make, and we only have so much time. Each product requires a different amount of space to store, and we only have so much space. So, taking all of these things into account, how many of each product can and should we make and sell to maximize profits? So, our feasible region is limited by space and time, as well as, for most application questions, negatives don't make sense, so the axes are also constraints. Because the optimization application questions deal with real-life scenarios, the -2 to 12 window won't always be large enough to view the entire graph. So one hint for choosing appropriate values for the y-max and the x-max is looking at the y-intercept of your lines. So for example, let's say our constraints are y is greater than or equal to 2x plus 45, y is less than or equal to -3x plus 500, and then x is greater than or equal to 0, and y is greater than or equal to 0. So finding the y-intercept of our lines, we know that one line crosses the y-axis at 45, and the other crosses the y-axis at 500. So a good starting value for the y-max is actually going to be like around 510, so just a little bit above the highest y-intercept. Now, choosing a good window is not an exact science, and there are many correct windows, so if you use like 505 or even 501, that would be fine. The important thing is that you can view all of the corner points of your feasible region. So looking at question number 1, a shawl requires 1 hour of spinning the yarn, 1 hour of dyeing the yarn, and 1 hour of weaving. An Afghan needs 2 hours of spinning the yarn, 1 hour of dyeing the yarn, and 4 hours of weaving. There are at most 16 hours for spinning, at most 12 hours for dyeing, and at most 28 hours for weaving. If each shawl sells for $30 and each Afghan for $50, how many of each shawl and Afghan should be made to maximize revenue? What is the maximum revenue? And we are letting x equal the number of shawls and y equal the number of Afghans. So on application questions, I think it helps to organize the information into a table. So x is the number of shawls and y is the number of Afghans. And then I'm going to have a totals column. Okay, so what types of information are they giving us? They are talking about spinning the yarn, dyeing the yarn, weaving, as well as selling. So we have spinning, dyeing, weaving, and selling. So the types of information, I'm going to put that on the side. So a shawl requires 1 hour of spinning, 1 hour of dyeing, 1 hour of weaving, and it sells for $30. So that's going to be my column. 1, 1, 1, and 30. And then an Afghan needs 2 hours of spinning, 1 hour of dyeing, and 4 hours of weaving. And those sell for $50. Okay, what else do we know? We know that there are at most 16 hours for spinning. So this has to be less than or equal to 16, because it can be at most 16. There are at most 12 hours for dyeing, so this is less than or equal to 12. There are at most 28 hours for weaving, so less than or equal to 28. And then finally, we are trying to maximize the revenue. So I'm going to put max here. Next, I want to translate my table into my equations. So these are going to be my coefficients of my x's. These are going to be my coefficients of my y's. And then these three are going to be on the other sides of the inequalities. The one that says max, this actually tells us that the 30x plus 50y is our objective function. So this is the one that we are trying to maximize. So we're not actually going to graph this, we're just trying to maximize it. But the other three, those are constraints. We need to graph those. So this first one is going to be 1x plus 2y is less than or equal to 16. And whenever it's a 1, we don't actually need to put the 1. So x plus 2y is less than or equal to 16. The second one is x plus y is less than or equal to 12. And then the third one is x plus 4y is less than or equal to 28. So there's actually two more inequalities that we need, and they're not found in the problem, but we need to know to put them. And that would be x and y both have to be greater than or equal to 0. So this is because of real life, meaning we don't want to have to deal with negative numbers in this problem. Okay, so I need to graph my lines so I can find my feasible region. So I need to solve for y in these three inequalities. So x plus 2y is less than or equal to 16. I want to subtract x from both sides, and then divide both sides by 2. So y is less than or equal to negative 1/2 x plus 8. The next one is x plus y is less than or equal to 12. If I just subtract x from both sides, then y is less than or equal to negative x plus 12. And then lastly, x plus 4y is less than or equal to 28. I want to subtract x from both sides, and then divide both sides by 4. So y is less than or equal to negative 1/4 x plus 7. So I'm going to be graphing these three lines as well as y is greater than or equal to 0. So we can't graph the x one, we have to do that by hand. So I'm ready to graph my lines on my calculator. So if I go to the y equals menu and type them into y1 through y4, I actually do want to change my window. And I know that my highest y-intercept is 12. So if we go to the window, I'm going to change my y-max and my x-max to be a little bit bigger than 12. So let's try 14. Again, it's not an exact science. And this is what our graph looks like. Next, I'm ready to do the shadings. And I like to do the reverse in the shadings because I think it's easier to look at. So my first three inequalities were all less than or equal to. But because I'm doing the reverse, I want to pick the upper triangle or the upper shading for these. And then for the y is greater than or equal to 0, I'm going to choose the lower shading. So if we press graph, this is our feasible region. And again, manually we need to cut off this because x has to be greater than or equal to 0. So we can't have negatives. So my feasible region is going to be right here. Now I do want to calculate the intersection points, and it's going to help to remove the shading while I'm doing that. So if we go to y equals and change these all back to the line symbol and then regraph it, we can find our intersection points. Before we find the intersection points on the calculator, I want to draw the graph on our paper. So it's going to look something like this. And this is our feasible region. And we have 5 corner points that we need to find. So now I'm finding the intersection points on the calculator. And I'm actually skipping some steps here, but if you want to see all of the steps of how to find the intersection point on the calculator, you can refer back to some of the previous videos. So the intersection points are 4, 6, 8, 4, 12, 0, and 0, 7. So now I want to label my corner points on my graph. We have 0, 0, 0, 7, 4, 6, 8, 4, and lastly 12, 0. So these are the points that I want to plug into the objective function. And I'm trying to find the maximum value. So if you plug in 0, 0, you get 0. If you plug in 0, 7, you get 350. If you plug in 4 and 6, you get 420. If you plug in 8 and 4, you get 440. And if you plug in 12 and 0, you get 360. So our answer is going to be the 440. But because this is an application question, we need to put some kind of context to this. So this means that the maximum revenue is $440, and this is at 8 shawls and 4 afghans.